There is a star dying right now, not metaphorically, not in some distant philosophical sense, literally right now. As you lie here in the dark, somewhere in the observable universe, somewhere in the vast and silent cathedral of space, a star is in the final minutes of its life. Its core has already begun to collapse. The light from that collapse won't reach us for millions of years, but the event is happening. It has already started. The clock is already running, and you will never see it coming. That's the thing about supernovae that nobody really talks about. We imagine the death of a star as something grand and announced, a cosmic alarm bell, a warning siren, a slow and dignified fade. We imagine there is time. But for the star itself, for the matter that has spent millions of years fusing hydrogen and helium and carbon and oxygen in a slow and magnificent dance of nuclear fire, the end comes in 7 minutes. The final chapter of a star that may be 1 billion times more massive than our Sun, a star that has burned for 10 million years, a star that has outlasted entire civilizations of worlds. That final chapter lasts 7 minutes. 7 minutes. The same amount of time it takes to boil an egg. The same amount of time a mediocre pop song plays on the radio. The same amount of time you might spend deciding what to watch before you finally give up and go to sleep. 7 minutes is nothing. 7 minutes is a rounding error in a human life. And yet inside those 7 minutes is contained one of the most violent and energetic events the universe is capable of producing. Inside those 7 minutes, a star tears itself apart and briefly outshines entire galaxies. Tonight, we're going to go inside those 7 minutes. We're going to start at the very beginning. Not just the 7 minutes, but the millions of years that built up to them. Because you cannot understand the end without understanding everything that came before it. We're going to walk through the entire life of a massive star, phase by phase, until we arrive at the moment the core crosses the threshold of no return. And then we're going to slow time down. We're going to stretch those 7 minutes out and walk through them second by second, beat by beat, layer by layer, until you understand exactly what happens when a star decides to end. By the time we're done, you'll never look at the night sky the same way again. Because the stars you see up there, the ones that look so permanent, so fixed, so eternal, they are not eternal. They are all on clocks. And some of them right now are closer to their final 7 minutes than you would ever feel comfortable knowing. Let's begin a long time before the end. Let's begin with a cloud. Somewhere in a galaxy. It could be ours, it could be one of the 2 trillion others scattered across the observable universe. There is a nebula, a vast, cold, diffuse cloud of hydrogen, gas and dust stretched across hundreds of light years, drifting slowly through the interstellar medium. It has been there for a very long time. It is not doing much, it is not burning, it is not collapsing. It is simply existing in the way that cold gas clouds exist, slowly, patiently, unremarkably. But something disturbs it. Maybe it is the shockwave from a nearby supernova, the death of another star, sending a ripple of compressed gas outward through the galaxy at thousands of kilometers per second. Maybe it is a collision between 2 spiral arms of the galaxy as it rotates. Maybe it is the gravitational tug of a passing star cluster. Whatever the cause, some part of the cloud begins to compress. Gravity, always gravity, begins to do its work. The compressed region pulls more gas toward it. More gas means more gravity means more compression. The process is slow at first, millions of years slow, but it is self-reinforcing, and it does not stop. This is called gravitational collapse, and it is the first step in the birth of every star that has ever existed. As the cloud collapses, it heats up. This is basic physics. When you compress a gas, the particles inside it have less room to move, and that confinement manifests as heat. The center of the collapsing cloud gets hotter and hotter as more and more material falls inward. It begins to glow, not from nuclear fusion yet, just from the heat of compression, the same way a bicycle pump gets warm when you use it. This early glowing object is called a protostar, and it is not yet a star. It is a star waiting to be born. The protostar continues to collapse, continues to heat. The surrounding gas continues to fall inward, and as it does, conservation of angular momentum causes the whole system to spin faster, the same way a figure skater spins faster when she pulls her arms in. A spinning disk of gas and dust forms around the protostar. This disk will eventually become planets. But we're not here tonight to talk about planets. We're here to talk about the star at the center. The protostar collapses for thousands of years, for hundreds of thousands of years. And then, at some point, when the temperature at its core reaches approximately 10 million degrees Kelvin, something changes, something ignites, hydrogen fusion begins. This is the moment of stellar birth, the moment when the outward pressure of nuclear fusion, protons slamming into each other hard enough to overcome their mutual electromagnetic repulsion and fuse into helium nuclei, releasing energy in the process, balances the inward pull of gravity. The star stops collapsing. It finds an equilibrium. It settles into the long, stable burning phase that will define most of its life. For our star, the massive one, the one we're here to talk about tonight, that equilibrium begins at a core temperature far higher than what you'd find in a star like our Sun. Our massive star is 10, 20, maybe 50 times the mass of the Sun. That extra mass means extra gravity. That extra gravity means extra pressure on the core. That extra pressure means higher temperatures. Higher temperatures mean faster, more energetic fusion reactions. And faster, more energetic fusion reactions mean the star burns through its fuel at a breathtaking rate. This is the central tragedy of massive stars. The more massive a star is, the shorter its life. A star like our Sun will burn for about 10 billion years. A star 20 times more massive will burn through its hydrogen in perhaps 10 million years. A star 50 times more massive might last only a few million years. In stellar terms, these are mayfly lifetimes. They are born bright and furious. They burn at temperatures that make our Sun look timid. They blaze with a luminosity millions of times greater than the Sun, and they die young. But during their short lives, they are the most spectacular objects the universe produces in terms of raw energy output. A massive O-type star, the kind of star we're discussing tonight, radiates so intensely that it can ionize the gas around it for dozens of light years in every direction. It blows the surrounding nebula away with its stellar wind. It shines blue-white at temperatures of 30, 40, 50,000 degrees at its surface, while its core reaches temperatures measured in hundreds of millions of degrees. It is a reactor running at maximum power, and it cannot slow down. And because it cannot slow down, it burns through its hydrogen faster than it can afford to. The main sequence phase of the long, stable hydrogen-burning phase that defines a star's youth and middle age lasts, for our massive star, somewhere between 3 and 10 million years, depending on its exact mass. For most of that time, the star is relatively stable. The core is fusing hydrogen into helium. The energy released by that fusion creates an outward pressure that holds up the star's enormous weight. The star is in balance. It is burning, yes, but it is burning steadily, and the balance holds. But hydrogen is finite. Slowly, over millions of years, the hydrogen in the core is consumed. The helium that replaces it doesn't fuse at the temperatures the core is currently running at. Helium needs higher temperatures to fuse, temperatures that hydrogen fusion cannot produce. So as the hydrogen runs low in the core, the fusion reactions begin to slow. The outward pressure begins to decrease. Gravity, which has been held at bay for millions of years, begins to win again. The core starts to contract, and as it contracts, it heats up. The outer layers of the star, still rich in hydrogen, begin to fuse in a shell around the contracting helium core. The extra energy from this shell fusion pushes the outer layers of the star outward. The star begins to expand. It swells. Its surface cools as it expands, turning from blue-white to yellow, to orange to red. The star has become a red supergiant. A red supergiant is an almost impossible object. Stars like Betelgeuse, the bright red star in the shoulder of Orion that you can see from your backyard on a clear night, are red supergiants. If you placed Betelgeuse where our Sun is, its surface would extend beyond the orbit of Jupiter. Some red supergiants would reach past the orbit of Saturn. These are objects so large that if you were standing on a planet orbiting at the distance of Mercury, the star's surface would fill the entire sky. They are enormous, diffuse, and relatively cool at their surfaces, but inside, in the contracting core, something very different is happening. The helium core, squeezed by gravity and heated by the compression, eventually reaches the temperature needed to fuse helium, approximately 100 million degrees. And so, a new phase begins, helium fusion. The core ignites again. Helium fuses into carbon and oxygen. The outward pressure from helium fusion stabilizes the core again, but only briefly, because helium burns even faster than hydrogen. The core runs through its helium in a fraction of the time it took to burn through the hydrogen. A few 100,000 years at most, and when the helium is gone, the core contracts again. You can see where this is going. Each successive fuel burns faster. Each successive fuel requires higher temperatures to ignite. Each successive fuel produces a core contraction, followed by a shell-burning phase, followed by another expansion of the outer layers. The star is layering itself. By the time we get to the final stages of stellar evolution, a massive star has developed an interior that looks, in cross-section, like an onion. The outermost layer is still mostly hydrogen. Below it is a shell of hydrogen fusion. Below that is a layer of helium. Below that is a shell of helium fusion. Below that is a layer of carbon. Below that, carbon fusion has started, carbon fusing into neon, magnesium, and sodium at temperatures of around 500 million degrees. Below that, neon and oxygen are fusing. And at the very center, at the innermost core of the star, surrounded by all these concentric shells of burning gas, something even more extreme is happening. Silicon is fusing. Silicon fusion is the last stage. It is where the story reaches its end, because silicon fusion produces iron, and iron is where stellar nucleosynthesis stops. Here is the reason, and it is important. Throughout the entire history of this star, through millions of years of hydrogen fusion, helium fusion, carbon fusion, neon fusion, oxygen fusion, silicon fusion, every single fusion reaction has released energy. That energy is why the star shines. That energy is what holds the star up against its own gravity. Every time two lighter nuclei fuse into a heavier one, a tiny amount of mass is converted into energy, according to Einstein's famous equation. The star is living off the profit of nuclear fusion. The universe is, in a sense, paying the star to exist. But iron is different. Iron is the most stable nucleus in the universe. It sits at the bottom of a valley in what physicists call the nuclear binding energy curve. To fuse two iron nuclei into something heavier does not release energy. It requires energy. Iron fusion is not a profit, it is a cost. If the core tries to fuse iron, it doesn't generate the pressure needed to hold itself up. It consumes energy instead. And so, when the silicon in the core is exhausted and the core becomes iron, the star has reached the end of its fuel. Not just its current fuel, all of its fuel, every trick it had, every nuclear reaction it could run. The iron core sits there, inert, held up only by quantum mechanical pressure. Specifically, electron degeneracy pressure, the quantum mechanical resistance of electrons to being crammed too close together. And the iron core grows because the silicon-burning shell surrounding it continues to rain iron down onto it, and the iron core accumulates mass faster and faster. The silicon shell burns through its fuel in approximately 1 day. 1 day for a massive star in silicon fusion, after millions of years of hydrogen burning, hundreds of thousands of years of helium burning, hundreds of years of carbon burning, a year of oxygen burning. Silicon burning lasts 1 day, and at the end of that day, the iron core crosses a threshold. The Chandrasekhar limit, approximately 1.4 times the mass of our Sun. This is the maximum mass that electron degeneracy pressure can support. When the iron core exceeds this limit, electron degeneracy pressure fails. It simply cannot hold anymore. And with nothing to hold up the core against the crushing weight of the entire star above it, against the gravity of an object 20, 30, 50 times the mass of the Sun, the core begins to collapse. Not slowly, not gradually, not over millions of years or thousands of years or even hours. The collapse happens in seconds. In the next quarter of a second, the iron core, which is roughly the size of Earth, about 12,000 kilometers across, collapses to something approximately 20 kilometers across. 20 kilometers, the size of a city. The entire core of a star more massive than you can comprehend compresses to something smaller than the distance from one end of a metropolitan area to the other. And this is where the 7 minutes begin. Minute 0. The core crosses the Chandrasekhar limit. Nothing in the universe above the star knows what is about to happen. The star's surface, hundreds of millions of kilometers away, is still glowing red, still fusing silicon in its outer shells, still doing everything a massive red supergiant does. The light leaving the star's surface right now will still be showing a living star for weeks after the collapse begins. The information, even traveling at the speed of light, cannot escape outward. Faster than the collapse proceeds inward, the collapse begins. In the first fraction of a second, the iron core is in free fall. Every atom of iron, every nucleus, every particle of matter in the core is falling inward simultaneously. The collapse is not happening at the edges and working its way in. The entire core, a sphere the size of Earth, is collapsing at once. The speed of collapse approaches 1/4 of the speed of light. In the first tenth of a second, the core has already compressed to something far smaller than it was. The density is rising. The pressure is rising. The temperature is rising. At around 10 trillion degrees, temperatures not seen in the universe since the first second after the Big Bang, something new begins to happen. The iron nuclei, which have been intact since they were forged by silicon fusion, begin to disintegrate. The photons in the core at these temperatures are so energetic, so gamma-ray intense, that they smash the iron nuclei apart. Disintegration, it's called. Iron nuclei break apart into helium nuclei and free neutrons and protons. All that energy that was locked up in the structure of those nuclei, all those millions of years of stellar nucleosynthesis, undone in milliseconds. The iron that the star spent its entire silicon-burning phase creating is destroyed in a tiny fraction of a second. This costs energy, a catastrophic amount of energy, and that cost accelerates the collapse further. The protons in the core, freed from their nuclei, surrounded by an increasing density of electrons, begin to interact with those electrons. Proton plus electron becomes neutron plus neutrino. This process is called neutronization or electron capture. The electrons that were providing the degeneracy pressure that had been holding up the core, those electrons are being absorbed, removed from the equation. The last remaining force holding the core up is being consumed from within, and neutrinos, those almost massless, almost non-interacting ghost particles that normally pass through matter as though it doesn't exist, are being produced in incomprehensible numbers. In the first second of the collapse, the collapsing core produces more neutrinos than the Sun will emit in its entire 10 billion year lifetime. The energy carried by those neutrinos is roughly equivalent to the gravitational binding energy of the entire neutron star, approximately 3 times 10 to the power of 46 joules, a number so large it is essentially meaningless in human terms. Normally, neutrinos don't interact with the matter. You could stack a light year of lead between you and a neutrino source, and most of the neutrinos would still get through. But the core of a collapsing star is no longer normal matter. It is matter compressed to densities that exceed that of an atomic nucleus. At these densities, even neutrinos cannot escape freely. They are momentarily trapped, and their trapping matters enormously, as we will see. The collapse continues. Within a second, the inner core, perhaps half a solar mass of material, has compressed to nuclear density, approximately 250 million metric tons per cubic centimetre. This is the density at which protons and neutrons are essentially touching each other. This is the density of an atomic nucleus, and at this density, a new force asserts itself. The strong nuclear force, but the fundamental force that holds nuclei together, becomes repulsive at very short range. When neutrons are crammed close enough together, the strong force pushes back. Hard. Very hard. Nuclear matter is almost incompressible at these densities, and the collapsing inner core suddenly, violently, abruptly stiffens. The inner core bounces. This is called the core bounce, and it happens within the first second of the collapse. The inner core, falling inward at a quarter of the speed of light, hits the wall of nuclear incompressibility and rebounds outward. A shockwave, an outward propagating pressure wave, moving at a significant fraction of the speed of light, launches from the surface of the newly formed proto-neutron star and begins to propagate outward through the still infalling outer core. This shockwave is the beginning of the supernova explosion, but it is not yet enough to actually blow the star apart. Here is one of the most fascinating and deeply counterintuitive things about core collapse supernovae. The shockwave generated by the core bounce is not, by itself, powerful enough to explode the star. It stalls, As the shockwave moves outward through the still infalling iron core, it loses energy by dissociating the iron nuclei it passes through, undoing them, breaking them apart, which costs energy just as photodisintegration did moments earlier. By the time the shockwave has travelled a few hundred kilometres from the proto-neutron star, it has lost so much energy that it is no longer a shockwave. It has become a standing accretion shock, a bubble of hot gas, stalled, sitting at a radius of perhaps 100 or 200 kilometers from the center, being slowly battered down by the infalling outer core material raining through it from above. For a few hundred milliseconds, a fraction of a second, the universe hangs in the balance. The stalled shock is being pushed inward by infalling matter. It needs something to revive it, something to pump energy back into it, something to push it outward before the entire star collapses into a black hole. And what saves it is the neutrinos. Remember the neutrinos, the inconceivable flood of neutrinos pouring out of the proto-neutron star, carrying with them an amount of energy equivalent to the sun's entire 10 billion year output every fraction of a second. Most of those neutrinos will pass through the star and through the galaxy and through the universe and never interact with anything again. But the stalled shock is sitting in a region of extremely high density. And even though neutrino interactions are incredibly rare when you have this many neutrinos hitting this dense A region, even a tiny fraction of energy transfer matters. Neutrino heating. A small percentage, perhaps a few percent, of the neutrino flux is absorbed by the material behind the stalled shock. That absorbed energy heats the gas. Heating the gas increases the pressure behind the shock. Increased pressure pushes the shock outward. The shock revives. This process, the neutrino-driven revival of the stalled accretion shock, is currently one of the most active areas of research in theoretical astrophysics. It is extraordinarily difficult to model because it involves general relativity, neutrino transport, fluid dynamics, and nuclear physics, all operating simultaneously in 3 dimensions. Supercomputer simulations have been running for decades trying to capture the full complexity of what happens in those first few seconds. And while our understanding has grown enormously, there are still details being worked out. But the observational evidence is overwhelming. It works. Because supernovae happen, because we see them, the shock revives and it begins to move outward. Minute 1. The shock is moving. The revived shock is now propagating outward through the layers of the star. It is not moving at the speed of light. It is moving at a significant fraction of the speed of light in the very inner regions. But as it travels outward through denser and denser material, it slows. By the time it reaches the outer shells of the star, it will have slowed considerably. But it is moving. It is unstoppable. It is carrying an energy of approximately 10 to the power of 44 joules, about 100 times the total energy the Sun will radiate over its entire 10 billion year lifetime. Let that sink in. The explosion of a single massive star releases, in the form of kinetic energy in the shock wave, roughly 100 times the entire energy output of a star like our Sun over 10 billion years. And that's not even counting the neutrinos, which carry away roughly 100 times more energy still. As the shock moves outward, it passes through the silicon shell, the oxygen shell, the neon shell, the carbon shell, the helium shell. Each layer it passes through is compressed and heated past the point of nuclear fusion, even for elements that wouldn't normally fuse. The shock passage triggers explosive nucleosynthesis in each layer it crosses. New elements are forged in the shock front: calcium, titanium, chromium, manganese, nickel, and radioactive nickel-56, which will later decay into cobalt-56 and then iron-56, producing the light that makes the supernova glow for weeks and months after the explosion. The elements that make up your body and the calcium in your bones, the iron in your blood, the oxygen you breathe, the carbon that forms every molecule of every cell, much of this was forged either in the quiet fusion of long-dead stars or in the explosive nucleosynthesis of moments exactly like this one. The shockwave passing through a dying star is a forge. It is the most productive nuclear reactor in the universe, and it is moving outward. The star above the shock still doesn't know what's happening. The surface of the star, still glowing red, still enormous, is not yet responding to the shock racing upward through its interior. The surface is calm. The surface will be calm for minutes more. The shock is still inside the star. Minute 2. Deep in the interior, the shock wave has now passed through the iron core region entirely and is well into the silicon and oxygen layers. In its wake, it has left the proto-neutron star, a city-sized sphere of neutrons rotating perhaps 30 or 40 times per second, radiating neutrinos at an almost incomprehensible rate, its surface temperature around 100 billion degrees, its density so extreme that a teaspoon of its material would weigh roughly 1 billion tons on Earth. The proto-neutron star is quietly consolidating itself. Neutrinos continue to pour from it. The neutrino luminosity at this moment is roughly 10 to the power of 46 watts. 10 trillion watts. For comparison, the total luminosity of all the stars in the observable universe combined is estimated at around 10 to the power of 49 watts, so the proto-neutron star is emitting roughly 0.1% of the luminosity of the entire observable universe, in neutrinos alone, from an object the size of a city. This continues for approximately 10 seconds. In the first 10 seconds after the bounce, the proto-neutron star radiates more energy as neutrinos than every star in every galaxy that has ever existed in the history of the universe since the Big Bang, combined, has radiated as light. Neutrinos detected from supernova 1987A, an actual supernova observed in the Large Magellanic Cloud, a dwarf galaxy orbiting the Milky Way, in February 1987, confirmed this theory. 24 neutrinos were detected by 3 neutrino observatories around the world in the seconds surrounding the optical brightening of that supernova. 24 individual neutrino detections out of the incomprehensible flood that passed through Earth confirmed a theory that had been developed over decades of mathematical reasoning. 24 particles, confirming the deaths of stars. Meanwhile, inside the exploding star, the shock continues its outward march. It is encountering the denser outer layers now, and where the density gradient changes, it triggers instabilities, turbulence, mixing. The different layers of the star, which had been carefully stratified by millions of years of stellar evolution, each layer sitting quietly above, the last in neat onion shell order, are being violently mixed by the shock. Hydrogen from the outer layers falls inward through the shock. Oxygen and carbon from deeper layers are thrown outward. The careful architecture of the star's interior is being scrambled. This mixing is why the heavy elements forged in supernovae end up distributed throughout the expanding remnant, available to be swept up into new stars and planets, and eventually into the bodies of living things. If the layers didn't mix, if the iron and nickel and calcium stayed neat and stratified, they might stay trapped in the neutron star or fall back into a black hole. The turbulent violence of the explosion is what seeds the universe with the raw materials of chemistry and life. Minute 3. A crack of light. The shock wave is now approaching the helium layer of the star. Below it, the silicon and oxygen shells have been detonated. Above it, vastly above it, hundreds of millions of kilometers above it, the surface of the star is still glowing placidly in the night. Still a red supergiant, enormous and red and slow. But something is beginning to happen at the surface. Neutrinos. The flood of neutrinos from the proto-neutron star is so intense, and the star's outer layers are being so thoroughly penetrated, that even the tiny fraction of neutrino energy deposited in the stellar envelope is beginning to make a difference. Not in any visible way yet, not dramatically, but the temperature in the outer layers is ticking upward, slightly. The pressure is increasing slightly, and ahead of the shock, travelling outward through the star at the speed of light, is a flood of X-rays and ultraviolet photons. As the shock moves inward, layers and heats them to extreme temperatures, the thermal radiation from that heated gas propagates outward through the star ahead of the mechanical shock wave itself. This radiation front, called the radiation precursor, moves through the star at the speed of light. It reaches the stellar surface before the shock does. This is called the shock breakout signal, and it is one of the most theoretically predicted but observationally difficult phenomena in astrophysics. In the moments before the mechanical shock wave itself bursts through the stellar surface, a brief, extremely bright pulse of X-rays and ultraviolet light escapes. It lasts for seconds to minutes, depending on the size of the star. And it is the first visible signal that a star is dying. We have caught this signal only a handful of times. It requires watching the right part of the sky at exactly the right moment, which, before modern survey telescopes, was essentially impossible. But the physics predicts it clearly, and in the instances where we have observed it, the data matches theory remarkably well. The radiation precursor is the first warning light. The stellar surface is about to experience something it has not experienced in millions of years: violent change. Minute 4. The star begins to know. The shock is in the helium layer now. It is still moving, still carrying its enormous kinetic energy, though it is spreading out over a larger and larger surface area as it expands, which dilutes its intensity per unit area. But the helium layer is being torn apart and heated as the shock passes through it. The helium does not fuse explosively the way the silicon and oxygen layers did. The conditions are not quite right, but it is heated to tens of millions of degrees as the shock passes. In its wake, the helium layer is expanding outward, away from the center. The star is beginning to blow itself apart from the inside. At the surface, the first effects of the radiation precursor are arriving. The outermost layers of the star, the hydrogen envelope, hundreds of millions of kilometers thick, diffuse and extended, are beginning to receive the first radiation from the hot, shock-heated interior. The temperature at the surface is beginning to rise. The star is beginning to brighten. Not dramatically yet, not explosively, but measurably, if you were watching with sensitive instruments. If you were orbiting this star in a spacecraft, you would notice something had changed in the last few minutes. The star below you would be getting slightly brighter. The character of its light would be shifting, becoming bluer, hotter, and there would be a faint, but detectable increase in X-ray emission from the stellar surface. Something is happening beneath that red surface. You would not know what, but you would know something. The shock is still minutes away from reaching the surface. Minute 5. Irreversible. There is no going back. There has been no going back since minute 0. But minute 5 is when the irreversibility becomes total in the mechanical sense. The shock wave has now reached the base of the hydrogen envelope, the star's outermost layer, and it is moving through relatively low-density material for the first time. When a shock wave moves through lower-density material, it accelerates. It picks up speed. What was already moving at thousands of kilometers per second is now moving faster. The hydrogen envelope, this vast, diffuse, outer shell of the star, is being pushed. The shock is driving it outward. The expansion has begun. The star is no longer a red supergiant in any meaningful sense. It is now an exploding object. The geometry of the explosion is set. The velocity of the ejector is set. The distribution of material that will form the supernova remnant is being determined right now, in this minute, by the details of how the shock propagates through the hydrogen envelope. Back at the center, the proto-neutron star has been settling. Its temperature is still incredibly high, still tens of billions of degrees at its surface, but it is beginning to cool. Not quickly. It will remain extraordinarily hot for decades, but the peak neutrino luminosity has passed. The rate of neutrino emission is declining. The proto-neutron star is entering a longer, quieter phase of cooling, settling toward its final configuration as a neutron star, an object that will persist, essentially unchanged, for longer than the current age of the universe. If it is massive enough, if enough material falls back onto it in the minutes and hours and days following the explosion, the proto-neutron star may not survive as a neutron star. It may collapse further, past even the quantum mechanical resistance of neutron degeneracy pressure, and become a black hole. This happens in some fraction of supernovae. The neutrino signal would end suddenly and completely. The explosion might be choked off. The star might implode in silence rather than explode in brilliance. But in our case, for our star tonight, the explosion succeeds. The neutrino energy was enough. The shock revived. The explosion is real. Minute 6. The surface cracks. The shock wave is now racing through the outermost layers of the hydrogen envelope. The density is dropping rapidly. The shock is accelerating, and the radiation that has been building up in the shock-heated gas behind the expanding stellar surface, photons that have been trapped in the dense interior, is now reaching the surface from below. The surface of the star is being hit simultaneously from two sides. The mechanical shock is arriving from below, pushing the surface material upward and outward. And the radiation, the flood of X-ray and ultraviolet photons building up in the heated interior, is arriving at the speed of light, ionizing the outer layers, heating them to temperatures far above anything they have experienced in millions of years of quiet burning. The shock breaks through. This is the shock breakout, the moment the shock wave punches through the surface of the star and erupts into space. It happens over a matter of seconds to minutes, depending on the size of the star, and it is one of the most energetic brief events in the universe. In the moment of shock breakout, the star briefly emits more energy in X-rays and ultraviolet light than the entire Milky Way galaxy emits in all wavelengths combined. A brief flare, a crack of light, the first visible signal of the death of the star, but visible only if you're watching at X-ray and ultraviolet wavelengths. To the naked eye, to someone watching from a distant planet with eyes adapted to visible light, The star hasn't visibly brightened yet. Not dramatically. The visible light brightening, the supernova, as seen in optical telescopes, comes later. It comes as the expanding shock-heated gas cools and the explosion develops over hours and days. But the X-ray flash is real. It is happening right now. If you had an X-ray telescope pointed at this star at this exact moment, you would see it flare to an almost incomprehensible brightness in a matter of seconds, and then begin to fade. The star has broken open. Minute 7. The end of the beginning. The shock has broken through the surface. The hydrogen envelope is expanding outward at thousands of kilometers per second. Material that was, 7 minutes ago, sitting quietly in the outer layers of a red supergiant, is now flying away from the center of the explosion at a velocity that would take it from Earth to the Moon in a matter of minutes. The ejector, the material thrown off by the explosion, will continue expanding for thousands of years. It will sweep up the interstellar gas surrounding the former star, creating a supernova remnant that will eventually span dozens of light years. It will be visible to astronomers if they happen to be looking at this part of the sky for tens of thousands of years. The light from the explosion will continue to brighten in visible wavelengths for weeks as the radioactive decay of nickel-56 and cobalt-56 in the ejector provides a long-lasting energy source. At peak brightness, the supernova may outshine the entire galaxy containing it. At the center, the proto-neutron star, or the black hole if it has already collapsed, sits in sudden quiet. The neutrino storm has peaked and is declining. The infalling material has been largely blown away by the explosion. For the first time in minutes, for the first time since the core collapse began, there is a kind of stillness at the center. Not peace exactly. The neutron star is still enormously hot, still radiating, still spinning rapidly. But the violence of the collapse is over. The explosion is done. Everything that will happen now, the expansion of the remnant, the fading of the optical light, the cooling of the neutron star over millions of years, is a consequence of these 7 minutes, a long tale of aftermath stretching out across cosmic time. But the event itself is over. 7 minutes. Let me tell you about something called SN 1987A. On the night of February 23, 1987, astronomers at several observatories in the southern hemisphere noticed something that had not been seen since 1604, a supernova visible to the naked eye. In a dwarf galaxy called the Large Magellanic Cloud, approximately 168,000 light-years from Earth, a star had exploded. The star was a blue supergiant called Sanduleak, minus 69 degrees 202. It was approximately 20 solar masses. It had been catalogued, studied, photographed. It appeared in archive images going back decades. And then it was gone, replaced by a brilliant point of light that brightened over weeks to a peak visible magnitude of around 2.9. Easily visible without a telescope from dark southern latitudes. SN 1987A, as it came to be known, taught us more about the mechanics of stellar death than any other event in modern observational astronomy. But perhaps the most important thing it gave us was the neutrino detection. Hours before the visible brightening of the supernova was noticed by optical astronomers, before any telescope was pointed at it, 3 neutrino detectors around the world recorded a burst of neutrino events. The Kamiokande 2 detector in Japan recorded 11 neutrinos in a 13-second window. The Irvine, Michigan Brookhaven detector in the United States recorded 8 neutrinos in 6 seconds. The Baksan Neutrino Observatory in Russia recorded 5 neutrinos, 24 neutrinos. 24 individual particle detections out of the incomprehensible flood of neutrinos that passed through Earth from the dying star. Each detector had been built to look for proton decay, a completely different phenomenon. They detected stellar collapse by accident, but those 24 particles confirmed everything. The timing, hours before the visible explosion, confirmed that the neutrinos emerged from the core collapse while the shock was still inside the star. The energies of the detected neutrinos were consistent with theoretical predictions for proto-neutron star cooling. The duration of the burst, roughly 10 seconds, matched predictions for the neutrino emission timescale. 24 particles across 3 detectors on one small planet, in a universe roughly 93 billion light-years across. And those 24 particles told us the entire story of what had happened 168,000 years earlier in the final 7 minutes of a star 20 times more massive than our Sun. This is one of the most astonishing things science has ever done, not because the equipment was sophisticated, though it was, not because the analysis was brilliant, though it was, but because it worked. Because the universe is consistent enough in its physical laws that a theory developed through pure mathematics and physics, without ever having observed a core collapse supernova in real time, correctly predicted what 24 particles would look like arriving at detectors built for a completely different purpose. SN 1987. A is still out there. It is still brightening and fading in complex ways. Its expanding shockwave is still moving outward through the gas and dust surrounding the former star. Radio and X-ray observatories continue to monitor it, and somewhere at its center, presumably, there is a neutron star, though it has not yet been directly detected, and some astronomers wonder if perhaps it collapsed into a black hole. The search for SN 1987A's compact remnant continues. It is, in a real sense, the most studied object in the sky. Now, let's go forward, because the 7 minutes are over, but the story isn't. The supernova remnant that forms in the aftermath of these 7 minutes is going to be with us for a very long time, and it is going to do things that matter, things that connect the death of this distant star to the existence of you lying here tonight, in the dark. The expanding shell of gas and dust from the explosion is moving outward at perhaps 10,000 kilometers per second in its fastest parts. Over decades and centuries, this shell sweeps up more and more interstellar material. It creates a structure we call a supernova remnant, a vast, tangled, beautiful nebula of glowing gas. The Crab Nebula, visible in the constellation Taurus, is the remnant of a supernova that exploded in 1054 CE, observed by Chinese and Arab astronomers. It is roughly 11 light-years across today, still expanding. At its center is the Crab Pulsar, a neutron star spinning 30 times per second, shooting beams of radio waves and X-rays into space with the regularity of a cosmic lighthouse. The Cassiopeia A remnant, the remnant of a supernova probably observed around 1680 CE, is one of the brightest radio sources in the sky. Its expanding shell shows the complex mixing and turbulence of the explosion still frozen in place, every filament and bubble telling the story of the instabilities that developed in the first seconds of the explosion. These remnants are beautiful. But they are more than beautiful, they are functional, they are the mechanism by which stars distribute the elements they spent their lives creating. Every heavy element heavier than iron in your body was created in a supernova explosion. Iodine, gold, silver, barium, strontium, uranium, every atom of these elements was forged in the extreme conditions of a stellar collapse, and then flung outward into space by the explosion. These elements drifted through space for millions or billions of years, mixing with gas clouds, eventually being swept into the nebulae that collapsed to form new stars and new planetary systems. The calcium in your bones was made in a dying star. The iron in your hemoglobin was made in a dying star. The oxygen you breathe, forged in stellar nucleosynthesis, distributed by stellar winds and supernova explosions. You are not merely observers of stellar death. You are, in a very literal and chemical sense, the product of it. The heavy elements in your body were created in the 7 minutes we just described. They survived the explosion. They drifted through space. They were incorporated into a nebula that collapsed 4.5 billion years ago to form our solar system. They fell onto the young Earth. They were incorporated into chemistry, into life, into you. You are stardust in the most literal possible sense. And the death that made you was violent and fast and 7 minutes long. Let's talk about what we don't know. Because as much as I've told you tonight, and we've covered an enormous amount, there is still deep uncertainty at the heart of this story. The mechanism by which supernovae actually explode is still not perfectly understood. This is not a minor caveat. This is a genuine, active, scientific puzzle that occupies some of the best astrophysicists in the world. The basic outline is established. Core collapse happens. The shock forms. The shock stalls. Neutrino heating revives the shock. The shock explodes the star. We know this sequence happens because we see supernovae, but the details of exactly how much neutrino heating occurs, how turbulence affects the shock revival, what role magnetic fields play, how the three-dimensional structure of the convection inside the proto-neutron star influences the outcome, these are still being actively researched. The first successful three-dimensional simulation of a core collapse supernova that actually exploded rather than stalling and failing to explode, was achieved only in the past decade. Simulating these explosions requires tracking the behavior of matter at nuclear densities, the transport of neutrinos through varying densities of matter, the three-dimensional turbulent fluid dynamics of the convection behind the stalled shock, the general relativistic effects of extreme gravity, all simultaneously, all in the same calculation. The simulations that have succeeded are some of the most computationally intensive calculations humans have ever performed. They require months of time on the largest supercomputers in the world to simulate a few seconds of stellar physics. And we still can't agree on all the details. One of the most intriguing open questions is why some stellar collapses produce supernovae, while others appear to produce black holes silently, what is sometimes called a failed supernova. In 2009, a red supergiant star designated N6946-BH1 in the galaxy NGC 6946 simply disappeared. It brightened briefly, consistent with what you'd expect in the early phases of a stellar collapse, and then faded to below detection limits. No supernova, no nebula, no neutron star detected. Just absence. The most likely explanation is that the collapse produced a black hole directly, and the explosion failed. The star ate itself. The neutrinos escaped, carrying away most of the energy, but the shock didn't revive, and the entire mass of the star, or most of it, fell into the newly formed black hole. How often does this happen? We don't know. Current estimates suggest that somewhere between 10 and 50% of stellar collapses might fail to produce visible supernovae, depending on assumptions about the progenitor mass and structure. If this is true, the night sky contains many stars that are quietly collapsing into black holes without the dramatic fireworks we've been describing tonight. The universe is stranger and more varied than our canonical stories suggest. There is another kind of supernova we should talk about because it operates on a completely different timeline and through a completely different mechanism, but the result is similarly violent and similarly important. The Type 1a supernova. A Type 1a supernova does not involve a massive star dying alone. It involves a white dwarf, the dead remnant of a star like our Sun, the end state of stellar evolution for most stars in the universe, being pushed past its limits by a companion star. When a star like our Sun reaches the end of its life, it does not explode. It puffs up into a red giant, it sheds its outer layers, and eventually the core is left exposed as a white dwarf, a dense, hot ball of carbon and oxygen roughly the size of Earth, supported by electron degeneracy pressure, no longer fusing, slowly cooling over billions of years. If that white dwarf exists in a binary system with another star, things can get complicated. The companion star might be a main sequence star, a giant, or even another white dwarf. If matter from the companion falls onto the white dwarf through mass transfer as the companion evolves and expands, or through stellar winds, the white dwarf's mass increases. And as its mass increases, it approaches the Chandrasekhar limit, the same limit we discussed earlier, the 1.4 solar mass limit beyond which electron degeneracy pressure cannot support the object. But for a white dwarf, crossing this limit doesn't produce a neutron star and a supernova. It produces something different. The white dwarf is made of carbon and oxygen. When it reaches the critical density and temperature, the carbon and oxygen don't disintegrate like the iron in a massive star's core. Instead, they fuse. Explosively, a thermonuclear runaway propagates through the entire white dwarf in seconds. The entire star, not just the core, but the entire object, is consumed by explosive nuclear burning. There is nothing left. No neutron star, no black hole. The white dwarf is entirely destroyed. What remains is an expanding cloud of radioactive nickel and iron and other elements racing outward at 10,000 kilometers per second. The reason Type 1a supernovae are so important to cosmology, and the reason they deserve mention here, is their remarkable consistency. Because the explosion is triggered at the Chandrasekhar limit, which is a fixed mass, and because the physics of the explosion is similar every time, Type 1a supernovae have similar luminosities. They are not identical. There is variation, but the variation is systematic and predictable. You can measure a Type 1a supernova's intrinsic luminosity from the shape of its light curve, its brightness over time. And if you know a supernova's intrinsic luminosity and you measure its apparent brightness from Earth, you can calculate its distance. Type 1. A supernovae are standard candles, cosmic distance markers that allow astronomers to measure distances across billions of light years with remarkable precision. It was observations of Type 1r supernovae in distant galaxies in the late 1990s that led to the discovery of dark energy, the discovery that the expansion of the universe is accelerating. This discovery, which earned the 2011 Nobel Prize in Physics, was one of the most transformative in the history of cosmology. And it depended entirely on dead white dwarf stars exploding in binary systems across billions of light years of space. The deaths of stars are how we measure the universe. The deaths of stars are how we know the universe is accelerating. The deaths of stars and the 7 violent minutes at the end of a stellar life are woven into everything we know about the cosmos. Let's talk about what's coming for our own sun. Because at some point in this contemplation, the question has to arise, what about us? What about the star we orbit? What about the thing that makes life on Earth possible? The sun is not going to go supernova. The sun is not massive enough. Stars that go supernova, core collapse supernovae, are stars roughly 8 solar masses and above. The sun, at 1 solar mass, is well below this threshold. It will die, but it will die quietly by stellar standards. It will die in a way that takes millions of years and ends not in a violent explosion, but in a slow fade. In about 5 billion years, a number so large it is essentially meaningless in human terms, the sun will exhaust the hydrogen in its core. It will follow the same evolutionary path we described for our massive star, except at a far slower pace. It will expand into a red giant growing large enough to potentially swallow Mercury and Venus, and perhaps Earth. Its outer layers will be ejected, forming a planetary nebula, a glowing shell of gas illuminated by the hot remnant core. And that remnant core will cool over billions of years as a white dwarf. No explosion, no neutron star, no shockwave. But that doesn't mean the sun is harmless. The sun's expansion into a red giant phase, which begins perhaps a billion years from now in a mild form as the sun slowly brightens on its main sequence, will eventually make Earth uninhabitable. The brightening sun will evaporate Earth's oceans. The runaway greenhouse effect will sterilize the surface. Long before the sun becomes a red giant, Earth may become a world inhospitable to life as we know it. But that's a different video. Tonight, we're here for the explosive kind of stellar death, the kind that happens in 7 minutes. One of the things that makes the 7-minute supernova so haunting is its invisibility. We have never seen a supernova begin. We have never watched a star transition from living to dying in real time. Every supernova we have ever observed has been discovered after the fact, after the explosion was already underway, after the shock had already broken out, after the visible light brightening had already begun. We watch the aftermath. We reconstruct the beginning from what we know of the physics. This is partly a numbers problem. The Milky Way produces perhaps 1 to 3 supernovae per century, based on estimates from the historical record and from observations of other galaxies. But most of these are hidden behind the dense dust and gas of the galactic plane, invisible in optical wavelengths. The last supernova clearly visible to the naked eye from Earth before SN 1987A was SN 1604, also known as Kepler's supernova, observed in 1604. Before that, SN 1572, Tycho's supernova. Both were in the Milky Way, both are still remembered as historically significant events. We are statistically overdue for a naked-eye Milky Way supernova. When it comes, if it comes in our lifetimes, modern neutrino detectors will see it hours before the visible brightening. Gravitational wave detectors, if they are sensitive enough, may detect the asymmetric motions of the collapsing core. X-ray satellites will catch the shock breakout signal, and then, perhaps, it will brighten enough to be visible in the daytime sky. Historical supernovae were visible in daylight. The brightest historical supernova ever recorded, SN 1006, was visible in daylight for months and may have been bright enough to cast shadows at night. The next Milky Way supernova, whenever it comes, will be the most studied astrophysical event in human history. Every observatory on Earth, in every wavelength, will be pointed at it. Every neutrino detector will be recording. Every gravitational wave interferometer will be straining for signal. It will tell us things we cannot currently predict. It will confirm theories we have spent decades building. And it will almost certainly reveal surprises we haven't yet imagined. The candidate everyone is watching most closely is Betelgeuse, the red supergiant in the shoulder of Orion, roughly 700 light-years away, is a massive, evolved star clearly near the end of its life, on astronomical timescales. In late 2019 and early 2020, Betelgeuse experienced a dramatic dimming, losing roughly two-thirds of its typical brightness over a period of weeks. Astronomers dubbed it the Great Dimming. And, for a few weeks, there was genuine excitement in the astronomical community about the possibility that Betelgeuse was finally about to explode. It wasn't. The dimming was caused by a large convective blob of material ejected from the stellar surface, cooling and condensing into dust, partially obscuring the star. A mundane explanation, well, mundane by red supergiant standards, for a dramatic observation. But Betelgeuse will explode on a time scale of somewhere between tomorrow and 100,000 years from now, which in astronomical terms is essentially the same thing as soon. When it does, it will be the most spectacular astronomical event in recorded human history. At roughly magnitude -12 at peak, brighter than the full moon, it will be visible in daylight. It will cast shadows at night. It will be visible for weeks or months. And the neutrino burst preceding the visible explosion will trigger alerts at neutrino observatories around the world in the seconds following the core collapse. At that distance, the X-ray and ultraviolet radiation from the supernova could damage Earth's ozone layer, increasing surface UV radiation and potentially affecting ecosystems. We are not in that zone. We are safe from Betelgeuse. But there are massive stars within a few hundred light-years of Earth. The question of nearby supernova hazards is a real one in astrobiology and planetary science. Some researchers have proposed that one or more supernova events in Earth's past may have contributed to mass extinctions, that the elevated radiation environment following a nearby stellar explosion may have played a role in the Ordovician extinction, perhaps 445 million years ago, or in other extinction events. The evidence is suggestive, but not conclusive. The universe, as it turns out, is not entirely indifferent to what happens on this small planet. The deaths of distant stars have shaped the history of life here, in ways we are only beginning to understand. 7 minutes. I keep coming back to that number. 7 minutes? In a universe that is 13.8 billion years old, in a galaxy that is 12 billion years old, in a star that lived for 10 million years. 7 minutes is the moment. Everything before it is prologue. Everything after it is aftermath. The explosion itself, the actual event, the core collapse and shock revival and breakout that defines a supernova, takes 7 minutes. There is something deeply humbling about this. We spend so much of our lives thinking that important things should take a long time. That significance is proportional to duration, that the bigger the event, the more time it should occupy. And here is the universe showing us otherwise. Here is the death of something that has existed for longer than our species has existed, something that has burned with the energy of 1,000,000 suns, something that has seeded the galaxy with the elements of chemistry and life, and its defining moment, the moment that separates what it was from what it becomes, takes 7 minutes. Less time than most of us spend in the shower, and the moment it's over, the consequences stretch outward forever. The neutron star will persist for longer than the current age of the universe. The expanding remnant will be detectable for hundreds of thousands of years. The elements thrown off in the explosion will drift through space for billions of years before finding their way into new stars and planets. The neutrinos from the explosion are already everywhere, already racing outward in all directions at the speed of light, and they will never stop. They will cross the observable universe. They will still be traveling long after the last stars have burned out and the universe has gone dark. 7 minutes, and then forever. There is one more thing I want to tell you tonight, one more thread to pull before we let this settle into the quiet dark. Somewhere in the universe right now, and given the size of the observable universe, this is not a metaphor. This is a statistical certainty. There is a planet orbiting a massive star. That planet may or may not have life on it. It may be a barren rock, or it may be a world with oceans and atmosphere and complex chemistry. It may have nothing on it that would recognize itself as alive, or it may have beings sophisticated enough to look up at their sky and wonder about the nature of the universe. And that planet is about to experience something none of its inhabitants can predict or prevent, because the star it orbits is about to go supernova. The core of that star has already been accumulating iron for days or weeks. The silicon shell is burning. The iron core is growing, approaching the Chandrasekhar limit. In some number of hours or days or weeks, the iron core will exceed 1.4 solar masses, and the collapse will begin. And when the shock breaks out of the stellar surface 7 minutes later, the planet, if it exists within the danger zone, within perhaps a few light years, will be bathed in a flood of X-rays and gamma rays intense enough to strip away its atmosphere, to sterilize its surface, to end whatever story had been developing there. We do not know if this is happening. We cannot see it. The light from the explosion has not reached us and may not reach us for millions of years. But the statistical arguments are clear. In a universe of 2 trillion galaxies, each containing hundreds of billions of stars, in a universe that produces perhaps 1 supernova per century per galaxy, there are supernovae happening right now, hundreds of thousands of them across the observable universe in this very moment. Some of them are ending worlds, and the worlds being ended, if they have inhabitants sophisticated enough to watch the sky, have at most seconds of warning. The neutrinos arrive first. If there are neutrino detectors, they might trigger. If the inhabitants have built instruments sensitive enough, they might see the X-ray precursor in their sky. But by the time the full explosion arrives, by the time the visible light and the gamma rays and the ultraviolet flood reaches them, there is nothing to be done. 7 minutes for the star, potentially seconds of warning for anyone watching. This is what the universe is, not cruel, because the universe has no intentions, not indifferent, because indifference implies a choice, simply physical, mechanical, following laws that do not care about the outcomes they produce. The massive star lives for 10 million years and dies in 7 minutes, and the consequences of those 7 minutes ripple outward through space and time without concern for who or what lies in their path. There is a kind of peace in this, if you let it in. Not the peace of safety, because the universe is not safe, but the peace of understanding, the peace of knowing the mechanism, the peace of lying here in the dark and recognizing that you exist in a universe that is old and violent and generous all at once, a universe that spends billions of years building the elements in stellar furnaces and then flings them outward in 7 violent minutes, so that other stars, other planets, other chemistries can inherit what was made. You are the inheritance of stellar death. Your body contains atoms forged in the cores of stars that lived and died before our solar system existed. Your iron was made in a supernova. Your calcium was made in a supernova. Your gold, if you're wearing any, was made in a neutron star merger, an even more violent event, even shorter in duration than the supernova we've been discussing tonight. Every heavy atom in you has a violent origin story. Every element that makes up the molecules that make up the cells that make up you was created in conditions that would instantly kill anything we recognize as alive. And yet here you are, alive, in the dark, on a small planet orbiting a middle-aged star in an unremarkable corner of one galaxy among 2 trillion. Made of stardust, and for now, for this particular moment in cosmic time, which is all any of us ever gets, here. The universe is currently approximately 13.8 billion years old. In that time, roughly 2 trillion galaxies have formed. Each galaxy contains, on average, hundreds of billions of stars. Each star, depending on its mass, will eventually die. Some quietly, as white dwarfs, some violently, as supernovae. The massive stars, the ones that produce core collapse supernovae, live only millions of years. So the universe has already seen the deaths of enormous numbers of them. The rate of supernovae in the universe has actually slowed since the early universe, when star formation was more intense and the proportion of massive stars was higher. But supernovae are still happening right now throughout the universe at a rate of many per second. Somewhere, every second, a star is dying in the same way we described tonight. Every second, somewhere in the observable universe, a core is crossing the Chandrasekhar limit. A shock is forming. A neutrino burst is propagating. A star is tearing itself apart in 7 minutes, and most of these events are happening too far away for us to ever know about them. The light from a supernova in a galaxy 10 billion light-years away might be detectable with our best telescopes. We have observed supernovae at cosmological distances, but the details, the specific star, the exact timeline, are lost to distance and the finite speed of light. We see the flash, we measure the spectrum, we infer the physics, but the individual story is invisible. The universe is full of stories we can never read. This is something astronomers live with constantly. The knowledge that the night sky is not a window into the present. It is a window into the past. Every photon that reaches your eye from a distant star left that star at some point in the past. A year ago, 1,000 years ago, 1,000,000 years ago, 1,000,000,000 years ago. The star you're looking at might not exist anymore. It might have exploded since that photon left it. You would not know. You cannot know until the light from the explosion reaches you, which it will, eventually, but not yet. Betelgeuse, which we talked about earlier, is roughly 700 light-years away. The light we see from Betelgeuse tonight left that star approximately 700 years ago. We are seeing Betelgeuse as it was in the 1300s. The star we're seeing existed when the Black Death was sweeping Europe, when the Mongol Empire was declining, when the Ming dynasty was founded. If Betelgeuse exploded 300 years ago, we wouldn't know yet. The light from that explosion wouldn't reach us for another 400 years. We are always looking into the past, always reading old light. And the universe is always full of events we can't yet see. The neutron star formed in our supernova tonight will have its own story, a long, quiet one, mostly. In the first seconds after the core bounce, the proto-neutron star is opaque. The density is so high that even neutrinos are trapped. Over the first 10 seconds, neutrinos slowly diffuse outward, and the proto-neutron star cools from temperatures of 100 billion degrees to something in the tens of billions of degrees range. Over the first minute, the proto-neutron star settles into something resembling its final configuration, a sphere of neutrons roughly 20 kilometers in diameter. The neutron star's surface temperature will remain in the millions of degrees for millions of years. During this time, it will be detectable as an X-ray source. It will pulse. Most neutron stars are pulsars, rotating rapidly and sweeping beams of radiation across space if its rotation axis and magnetic axis are misaligned. A rapidly spinning pulsar can rotate hundreds of times per second, beaming radio waves and X-rays with extraordinary regularity. The Crab pulsar, the neutron star at the center of the Crab Nebula, has been rotating 30 times per second for roughly 970 years since the supernova that created it. Its rotation is slowing, very gradually, as it loses energy to the electromagnetic radiation it emits. In millions of years, it will spin more slowly. In billions of years, it will spin slowly enough that its pulsar mechanism shuts off, and then it will simply cool, dimming over the eons until it is cold and dark and effectively invisible, a black dwarf neutron star drifting silently through the galaxy. Unless, of course, it finds a companion. Unless another star wanders close enough to be gravitationally captured, or unless the neutron star was born in a binary system and the companion survived the supernova explosion. Because neutron stars in binary systems can do extraordinary things, two neutron stars in a tight binary orbit will lose energy to gravitational wave emission, exactly the gravitational waves that LIGO and Virgo detect, and slowly spiral toward each other. Over millions or billions of years, they spiral inward, and when they finally collide, in an event called a neutron star merger, or a kilonova, the violence is extraordinary. The collision lasts milliseconds. It produces a short gamma-ray burst, detectable across the observable universe. It produces a gravitational wave signal so strong that LIGO detected one in 2017 from 130 million light-years away, event GW 170817. And it produces heavy elements through a process called rapid neutron capture. The R process, forging gold and platinum and uranium and dozens of other heavy elements in the incredibly neutron-rich environment of the merger. The gold in a wedding ring was made in a neutron star merger. The platinum in a catalytic converter was made in a neutron star merger. The uranium in nuclear reactors was made in a neutron star merger. Even in death, stars are making things. Even in the most violent events in the universe, core collapses, supernova explosions, neutron star mergers, the universe is manufacturing, building, creating new atoms, new possibilities, new chemical potential. The violence is not pointless. The violence is generative. We are near the end now, or near the end of what I can tell you tonight. The story itself has no end. It continues in the expanding remnant, in the cooling neutron star, in the heavy elements drifting through space, in the eventual formation of new stars and planets from the enriched material. The story goes on for billions of years, but our time tonight is drawing toward its close. Let me leave you with this. There are, right now, in the Milky Way galaxy, approximately 400 billion stars. Of those, perhaps a few dozen are candidates for supernova explosions in the astronomically near future, meaning within the next million years or so. Most of them are too far away to pose any danger. Some of them are being monitored by astronomers who track their brightness, their spectra, their variability, looking for signs of imminent collapse. They will not be found. The collapse will not be predicted. Not because astronomers are not trying, but because the physics of stellar interiors is still not perfectly transparent to our instruments, and because the final hours and days of a massive star's life, the silicon burning phase, the iron core growth, produce very little change in the star's external appearance. A star going supernova tomorrow would look, to a human observer, essentially the same as it did yesterday. We will not see it coming. And then some morning or some night, a neutrino alarm will trigger at a detector somewhere on Earth, and seconds to hours later, a point of light in the sky will begin to brighten, and the astronomical community will mobilize. Every telescope in the world will pivot, every satellite will reorient, and we will watch in real time as the light from a dying star 40,000 light-years away, or 70,000 light-years away, or perhaps only 1,000 light-years away, grows and brightens and eventually fades over weeks and months, and it will be the greatest natural spectacle in human history. And somewhere, in the expanding remnant, a neutron star will be born. And the elements scattered by the explosion will drift outward, and billions of years from now, those elements will be incorporated into a new solar system. And on some planet in that new solar system, if the conditions are right, chemistry will lead to biology, will lead to life, will lead to minds. And those minds, if they are curious, if they have the gift and the hunger to look up at the sky and wonder, might lie awake one night and think about where they came from. And they might understand eventually that they are made of the deaths of stars, that their iron and their calcium and their gold all have violent origin stories, that the universe, in its way, has been building toward them for billions of years through a cycle of stellar birth and violent death and new beginning, and they might feel, as I hope you feel right now, a strange and quiet awe. Not fear, not despair, but awe at the mechanism, awe at the scale, awe at the fact that 7 minutes, just 7 minutes, is enough to reshape a corner of the galaxy, enough to seed the interstellar medium with the elements of life, enough to create the conditions for everything that comes after 7 minutes. The universe is patient. It has been doing this for 13.8 billion years, and it will continue doing it for trillions of years more. There will be supernovae happening long after the sun has faded, long after Earth is gone, long after anything we recognize as human civilization has ended or transformed beyond recognition. The universe's stellar engines will keep running. The massive stars will keep living and dying and scattering their substance across the galaxy. And the galaxy will keep getting richer, heavier, more complex, more chemically interesting. Every supernova adds to the cosmic inventory. Every explosion enriches the interstellar medium. The universe is slowly building up a library of elements, and the librarians are dying stars. We are here because what happens after the 7 minutes, after the breakout, after the first light of the explosion reaches this planet, is a long story. A months-long brightening, a years-long afterglow, a centuries-long remnant, a millennia-long shockwave sweeping through the surrounding gas, and the slow, patient drift of the ejected elements through interstellar space. But tonight, I want to dwell here, at the edge, at the 2-minute mark, before the news arrives, because there is something in this threshold moment, this moment of knowing and waiting, that feels more true to the human experience of the universe than any other moment in this story. We are always in this position. We always know something is coming that we cannot stop. We always live in the gap between the event and the information. We always exist in the light of stars that may already be dead, looking up at a sky that is showing us the past, waiting for news that is already on its way. The universe is not cruel about this. It is simply large, simply old, simply consistent in its physics, which dictates that information cannot travel faster than light, which means the present state of the universe is always hidden from us. We see only the past. We receive only old messages. We live in a universe where the news from a dying star travels at 299,792 kilometers per second and still takes years or decades or millions of years to arrive. There is something comforting in this if you hold it right. The vastness that hides things from us is the same vastness that protects us. The stars that might explode and alter their surrounding neighborhoods are, in almost every case, so far away that their deaths are beautiful rather than dangerous. The universe is large enough that its violence is, for us, mostly spectacle, mostly wonder, mostly a reason to feel small and lucky and here. We are here, right now, in the dark, on this particular planet orbiting this particular star, in this particular moment, and the star above us, the one that will rise in the morning, the one that makes this life possible, is not in its final 7 minutes. It is not even close. It has 5 billion years of hydrogen left to burn, 5 billion years before its first evolutionary crisis, 5 billion years of yellow warmth and ordinary photons, and the patient conversion of hydrogen into helium in its core. We are not in the 7 minutes. We are in the deep middle of the story. And the deep middle is the good part. The deep middle is where living happens. Let me tell you about the supernovae we have seen, not inferred, not modelled, actually seen events that occurred close enough and at the right time for human observers to notice, to record, to wonder about. The historical record of naked-eye supernovae goes back at least 2,000 years. Chinese astronomers were meticulous recorders of astronomical phenomena. They called unexpectedly bright new stars guest stars, because they appeared in the sky uninvited and then eventually left. Their records, preserved and studied by modern historians of astronomy, give us a catalogue of probable supernova sightings extending back more than a millennium. The most famous entries in this catalogue are the supernovae of 1006, 1054, 1181, 1572, and 1604. SN 1006 is estimated to have been the brightest supernova in recorded history, and one of the brightest astronomical events ever recorded. It appeared in the constellation Lupus and was observed by astronomers and scholars across the world, in China, in Japan, in the Islamic world, in Europe, in what is now Switzerland, where a monk named Hepidanus recorded seeing a new star of unusual size appearing in the sky. At its peak, SN 1006 may have reached an apparent magnitude of -7.5, brighter than Venus at its brightest, brighter than anything except the Moon and the Sun. It was visible in full daylight. It cast shadows at night. It was, by any measure, extraordinary. SN 1054 gave us the Crab Nebula. Chinese and Arab astronomers recorded a bright new star appearing in the constellation Taurus on or around July 4th, 1054. It was visible in daylight for 3 weeks and remained visible to the naked eye at night for nearly 2 years before fading below naked eye visibility. What they were seeing was the explosion of a star roughly 6,500 light-years away. The expanding remnant of that explosion is now 11 light-years across. The Crab pulsar at its center, the neutron star formed in the collapse, pulses 30 times per second and is one of the most studied objects in the sky. Every time an astronomer points a radio telescope at the Crab pulsar, every time an X-ray satellite captures its rhythmic pulse, they are, in a sense, listening to the heartbeat of a star that died in the time of the Song dynasty. SN 1572, Tycho's supernova, named for the Danish astronomer Tycho Brahe, who observed it carefully, appeared in the constellation Cassiopeia in November 1572. Tycho was just 25 years old. He observed it for months, measuring its position with extraordinary precision for the era, demonstrating that it did not move against the background of stars, that it was not a comet or a nearby atmospheric phenomenon, but something genuinely among the stars themselves. His observations helped overturn the Aristotelian notion that the heavens were unchanging and perfect. A new star, appearing from nothing, was not compatible with a cosmology of perfect celestial spheres. Tycho's supernova helped crack open the old picture of the cosmos. SN 1604, Kepler's supernova, observed by Johannes Kepler and many others, appeared in the constellation Ophiuchus in October 1604. It was the last naked-eye supernova observed in the Milky Way. It remained visible for more than a year. Galileo observed it and used it in public lectures to argue against Aristotelian cosmology. Its remnant, Kepler's supernova remnant, is still expanding and still studied with X-ray and radio telescopes. And then nothing. For more than 400 years, no naked-eye supernova in the Milky Way, just the occasional supernova in distant galaxies, detectable only with telescopes, studied as data points rather than experienced as events. SN 1987A broke the silence in terms of neutrino detections and nearby galaxy supernovae. But it was not in the Milky Way. At 168,000 light-years, it was too distant to be more than a point of light, a bright one, visible to the naked eye, but not the kind of spectacle that a Milky Way supernova would produce. The Milky Way is overdue. The statistics, based on supernova rates inferred from other spiral galaxies similar to the Milky Way, suggest that our galaxy should produce roughly 1 to 3 core collapse supernovae per century. In the past 400 years, we have had 0 detected ones. This does not necessarily mean we are overdue in a strict statistical sense. These events are random, and a 400-year gap, while unlikely, is not impossible. More likely, the explanation is that supernovae have been occurring but were hidden behind the dust and gas of the galactic plane, invisible at optical wavelengths. Our galaxy is not transparent. The dust that lies along the plane of the galaxy absorbs visible light almost completely over distances of a few thousand light-years. There could be, probably have been, several supernovae in our galaxy since 1604 that we simply couldn't see. But we would have detected the neutrinos from any supernova within the Milky Way with modern detectors. The fact that our current generation of neutrino detectors, Super Kamiokande in Japan, IceCube in Antarctica, and others, have not triggered a supernova alert since they were built suggests that no core collapse supernova has occurred in the Milky Way in the past few decades. They are waiting, the detectors are online, monitoring, watching. And when the neutrino burst comes, and whenever a massive Milky Way star crosses the Chandrasekhar limit, they will know within seconds. I want to spend some time with the elements, Because the story of supernovae is not only a story about light and fire and neutron stars, it is a story about chemistry, about the atoms that make the universe chemically interesting, about the reason that somewhere in the universe, and in fact, right here on this small planet, matter can organize itself into something complicated enough to wonder about its own origins. The universe in its first few minutes produced only hydrogen, helium, and trace amounts of lithium. That's it. Three elements with the vast majority of the matter being hydrogen and helium. A universe of only hydrogen and helium is a chemically boring universe. You cannot make DNA out of hydrogen and helium. You cannot make silicate rocks. You cannot make water. You cannot make the long chains of carbon compounds that fold and bend and interact in the extraordinary ways that biology demands. The heavy elements, everything heavier than helium, had to be made somewhere. And the answer, which took astrophysicists decades of work to work out in detail, is that they were made in stars. The lightest, heavy elements, carbon, nitrogen, oxygen, are made in the cores of stars through the main sequence and red giant phases. Carbon is made in red giants through helium fusion, nitrogen through the CNO cycle, oxygen through various stages of nuclear burning. These are the most abundant heavy elements in the universe, and they were made in the quiet, long-lived interior fusion of ordinary stars. The heavier elements, silicon, sulfur, argon, calcium, are made in the advanced burning stages of massive stars. The silicon burning phase that immediately precedes the supernova. These elements are made in the final, desperate fuel cycles of a star trying to stave off its own collapse. Iron, the most stable nucleus, the end point of stellar fusion, accumulates in the core until the core collapses. Iron is everywhere. It is the most common element in the core of Earth. It is in your blood. It was made in the silicon-burning cores of stars that lived and died before the solar system formed. The elements just above iron on the periodic table, cobalt, nickel, copper, zinc, are made in the explosive nucleosynthesis of the supernova itself. The shockwave passing through the star creates conditions hot and dense enough to produce these elements through rapid nuclear reactions. Cobalt-56 and nickel-56 are made in prodigious quantities and power the optical light curve of the supernova as they decay. Elements heavier than zinc, up through silver, cadmium, tin, and many others, are made through the S process, or slow neutron capture, which occurs in the helium-burning shells of evolved giant stars. These elements are built up gradually over thousands of years as nuclei absorb neutrons one at a time. And then there is a whole class of elements, the very heaviest ones, that cannot be made in any of these processes. They require an environment so neutron-rich and so energetic that it was only definitively identified in the past decade. We talked about it briefly earlier. Neutron-star mergers, kilonovae. When two neutron stars collide, the environment is so extraordinarily neutron-rich that the R process, rapid neutron capture, can build nuclei all the way up to uranium and beyond in a matter of seconds. Gold, platinum, lead, bismuth, uranium, thorium, all made in collisions between dead stars. The periodic table is, in this sense, a history of the universe. Each row and column tells you something about the processes and environments that created those atoms. The lightest elements were made in the Big Bang, the medium elements were made in stellar interiors, the elements around iron were made in the cores of massive stars, the slightly heavier elements were made in supernova explosions, The heaviest elements were made when neutron stars collided. Every atom in your body has a provenance. Every atom has a story that stretches back billions of years to some specific astrophysical event. The oxygen you breathe was made in the core of a star that exploded perhaps 6 billion years ago, and whose atoms drifted through space before being incorporated into the molecular cloud that became our solar system. The calcium in your bones was made in the silicon-burning shell of a massive star in its final hours before collapse. The iron in your hemoglobin, the molecule that carries oxygen through your blood, the molecule without which you could not use the oxygen you just breathed, that iron was made in the core of a star that collapsed and exploded in the same kind of event we have been describing tonight. You are not separate from the universe. You are not a visitor to the universe. You are not an observer of the universe. You are made of it. You are a local condensation of materials that were, until 5 billion years ago, scattered across light years of interstellar space. The stellar death that scattered them was violent. The journey they took through space was long. The process that assembled them into you was patient and slow and contingent on an extraordinary number of things going right. But here you are, an outcome, a product, a consequence of the final 7 minutes of a star you will never know, orbiting a galaxy you can barely see, in an event that happened long before your world existed. Let's travel now. Not in space, in time. Let's look at the far future of the thing we've been describing tonight. Let's follow the neutron star forward. It has been born in violence, formed in the collapse of an iron core, heated to 100 billion degrees, flooded the surrounding space with neutrinos, watched in a sense as the shockwave it helped revive raced outward and tore the rest of the star apart. Now it is alone. The explosion has thrown off the surrounding material. The supernova remnant is expanding outward. The neutron star sits at the center, spinning rapidly, perhaps dozens of times per second, perhaps hundreds, emitting beams of radiation from its magnetic poles. It is a pulsar. Its regular pulses of radio and X-ray emission tick across the universe like a cosmic clock. In the first 1,000 years, the neutron star is still hot enough to be detected as an X-ray source. Its surface temperature is in the millions of degrees. It is cooling, but slowly. The surrounding supernova remnant is still visible, still expanding, still glowing, still mixing the ejected material with the interstellar medium. If anyone is watching from a nearby world, and by nearby I mean within a few hundred light years, they would see the remnant as a glowing nebula, expanding and brightening in its own right. After 10,000 years, the supernova remnant has expanded to perhaps 30 or 40 light years across. The shock wave driving the expansion has slowed as it sweeps up more interstellar material. The central neutron star has cooled somewhat. Its surface temperature has dropped to below 1,000,000 degrees. The pulsar is still spinning, but slower than it was at birth. The rotation rate decreases as the pulsar loses energy to electromagnetic radiation. After 1,000,000 years, the supernova remnant has faded to the point of invisibility in most wavelengths. The neutron star has cooled to perhaps 100,000 degrees, still detectable with sensitive X-ray telescopes, but no longer the bright X-ray source it once was. Its pulsar mechanism may still be active. Some pulsars are detected with rotation periods of seconds or longer, indicating ages of millions of years. Others have slowed below the death line, where pulsar emission is no longer possible. After 1 billion years, the neutron star is cold and dark. Its surface temperature has dropped to perhaps a few thousand degrees, warm by neutron star standards, invisible to all but the most sensitive infrared detectors. It is spinning slowly. It has traversed a significant fraction of the galaxy in its billion-year journey. Neutron stars are often born with high velocities from the asymmetric nature of the supernova explosion, what we call natal kicks, and can travel hundreds of light years per million years. In a billion years, this neutron star may be far from where it was born, far from the planetary system that might have witnessed its birth, far from any object that knew the star it came from. It drifts. In 10 billion years, the neutron star is at room temperature, by any standard, or below. Colder than the cosmic microwave background, which has itself cooled significantly as the universe expanded. The neutron star is effectively invisible. It interacts with almost nothing. It is a city-sized sphere of neutrons, perfectly dense, perfectly stable, slowly cooling toward absolute zero. In 100 billion years, by which time the universe will be roughly 10 times its current age, the Sun will have long since faded to a white dwarf and then a black dwarf, and the era of star formation in most galaxies will be drawing to a close. The neutron star is still there, still drifting, still intact. The strong nuclear force holding its neutrons together is not going to weaken on any foreseeable timescale. Neutron stars, unless they gain mass and collapse into black holes or encounter some other catastrophe, may persist for astronomical timescales that dwarf anything we've discussed tonight. In 1,000,000,000,000 years, in the degenerate era, when the last red dwarf stars are burning out and the universe is populated mainly by white dwarfs, neutron stars, and black holes, our neutron star is still there, cold, dark, dense. In that era, most of the interesting physics in the universe will be happening in white dwarf and neutron star collisions, in the slow hawking radiation of black holes, in the occasional flicker of energy, when a white dwarf accretes just enough mass to trigger a thermonuclear explosion. The neutron star from our supernova tonight is, in that era, one of the most abundant types of object in the universe. In 10 to the power of 40 years, a timescale so large that the current age of the universe is a rounding error, there is speculation that proton decay may have reduced all ordinary matter, including neutron stars, to radiation and lighter particles. The physics here is uncertain. Proton decay has never been observed, and the timescale for it depends on which grand unified theory you believe. But if proton decay occurs, then on these timescales even neutron stars dissolve, and then there are only black holes and their slow, hawking radiation. And then, after timescales that make even proton decay look recent, even the largest black holes evaporate, and the universe grows cold and dark and nearly uniform. This is the heat death. Not a dramatic explosion, not a sudden ending, just a gradual, inexorable settling toward maximum entropy. A universe in which no more work can be done, no more concentration of energy, no more temperature differences to drive processes, no more stars, no more fusion, no more supernovae, no more 7-minute deaths that scatter elements across light years. Just quiet. We are nowhere near the heat death. We are in the stelliferous era, the age of stars, which by cosmological estimates will last another 10 trillion years. 10 trillion years of star formation, of fusion, of stellar evolution, of supernovae and neutron stars and white dwarfs and black holes, of chemistry and biology and whatever forms of complexity the universe has not yet invented. We are very early in the stelliferous era. The universe is only 13.8 billion years old. At the estimated duration of the stelliferous era, we are not even 1% of the way through the age of stars. There is time yet. There is so much time yet. I want to come back to Earth for a moment, to come back to this specific planet orbiting this specific star in this specific moment of cosmic history, because all of this, the collapsing cores and the neutrino floods and the shock waves and the scattered elements and the neutron stars drifting through the dark, all of it connects here. All of it is relevant here. Not in a metaphorical sense, in a chemical, physical, literal sense. The Earth is made of supernova ejecta. Not all of it. The hydrogen in the water of the oceans was present in the original nebula, inherited from the Big Bang. But the heavier elements, the silicon that makes up the silicate minerals of the mantle and crust, the iron that fills the core, the oxygen that combines with everything, the magnesium and aluminum and calcium and sulfur and all the rest, these are the products of stellar evolution and stellar death. These elements were made in stars that preceded the Sun, distributed into the interstellar medium by stellar winds and supernova explosions, gathered by the gravity of the collapsing solar nebula and concentrated into a planet. The Earth is, in a very real sense, a recycled star. And more than that, the Sun itself is a recycled star. The Sun is not a first-generation star. It contains heavy elements, iron, carbon, oxygen, silicon, in proportions that indicate it formed from material that had already been processed by at least one, probably several, previous generations of stellar evolution and death. The Sun is what cosmologists call a population 1 star, relatively young in cosmic terms, metal-rich, where metal means anything heavier than helium, formed from the enriched interstellar medium of a galaxy that had already been through many cycles of star formation and stellar death. The stars that came before the Sun, the stars whose deaths created the material from which the Sun and Earth are made, were population 2 or population 3 stars. Population 3 stars were the very first stars, formed from the pristine hydrogen and helium of the early universe. They were probably enormous, hundreds of solar masses, and they burned through their fuel in a few million years, and died in explosions that seeded the early universe with the first heavy elements. Population 2 stars, formed from this enriched material, lived out their lives, and in turn seeded the interstellar medium with more heavy elements. Population 1 stars, like our Sun, formed from the further enriched medium left by population 2 stars. The universe has been running these cycles of stellar birth and death for over 13 billion years. Every cycle enriches the interstellar medium further. Every supernova adds to the cosmic inventory of heavy elements. The universe is slowly, patiently building up the chemical complexity needed for planets and chemistry and biology. We are alive in the universe at a time when the interstellar medium is chemically rich enough for planets like Earth to exist. A planet like Earth, with its silicate mantle, iron core, water oceans, carbon-based life, requires all the elements that only exist because of billions of years of stellar evolution and supernova nucleosynthesis. If you ran the universe again but stopped it 3 billion years into its history, before multiple generations of stars had lived and died and enriched the interstellar medium, Earth-like planets would not exist. There wouldn't be enough heavy elements. We are alive at the right time. Not just in the stelliferous era, but after enough cycles of stellar death have occurred to make our kind of chemistry possible. We are chemical descendants of supernovae, alive in a universe that has cooked long enough to make us possible. The question that I suspect sits quietly underneath everything we've discussed tonight is this: are we alone? I don't mean in a dramatic science fiction sense, I mean in the chemical sense. In the sense that the story of supernovae and heavy element creation that we've been tracing tonight is the same story for every planet in the universe, around every star. The same nucleosynthesis, the same elemental abundance patterns, the same chemical starting points. Everywhere in the universe where there are stars, there are supernovae. Everywhere there are supernovae, there are heavy elements. Everywhere there are heavy elements, there is the potential for the kind of complex chemistry that leads to, well, to us. This is not a proof that life is common. The gap between having the right chemistry and actually producing life is enormous, and we don't fully understand how it was bridged even here on Earth. The origin of life remains one of the deepest unsolved problems in science, but it does mean that the prerequisite for life, the chemical raw materials, is not rare. It is scattered across the universe by the billions of supernova explosions that have occurred in the past 13 billion years. Every galaxy has been enriched by its stellar deaths. Every metal-rich star system has the chemical potential for planets like Earth. Whether that potential is commonly realized, whether life is everywhere or rare, or uniquely here, we do not know. We don't yet know of life anywhere except Earth, but the universe has been generous with the materials. The supernovae have been doing their work for billions of years. If life can emerge from the right chemistry, given the right conditions, given enough time, then the universe has provided abundantly. The question is ours to answer, and we are slowly building the tools and the knowledge to begin answering it. There is one more thing the death of a star teaches us, and it has nothing to do with physics or chemistry or biology. It has to do with what it means to exist at all. A massive star lives for 10 million years. In those 10 million years, it burns. It burns with a luminosity that dwarfs anything we are capable of producing or even imagining on human scales. It fills its neighborhood with light and radiation and stellar winds. It ionizes the gas around it for dozens of light years. It is, in every measurable sense, spectacular. And then it dies in 7 minutes. Not slowly, not peacefully, not with warning. In 7 minutes, everything it was, every million tons of matter, every erg of energy, every gram of hydrogen and helium and carbon and oxygen, is either collapsed into an object the size of a city or thrown outward in an explosion that will travel for thousands of years. What the star leaves behind is more than what it was. The neutron star at its center is a new kind of object, denser than anything that preceded it. The expanding remnant is richer in heavy elements than the gas from which the star formed. The galaxy is more chemically complex for having had this star live and die in it. The universe, in a very specific and measurable sense, is better for what this star was and what this star became. This is not sentimentality. This is physics. The star made things. It made elements that did not exist before it formed. It distributed those elements, and the explosion, the violent, 7-minute death, is what made the distribution possible. Without the explosion, the elements would stay locked in the neutron star or fall back into a black hole. The violence is necessary. The death is the point, in a functional sense, of the life. I do not draw easy lessons from this. I do not think the lives of stars map neatly onto the lives of people, or that cosmic processes tell us how to grieve or how to think about our own mortality. The universe is not a parable. It does not arrange its physics to teach us things. But I do think there is something in the fact that the death of a star is not only an ending, it is a making. The 7 minutes of the supernova are 7 minutes of extraordinary creation. The creation of new elements, the creation of a neutron star, the creation of the conditions under which new stellar systems will one day form. The destruction is generative. The ending is a beginning. Not metaphorically, physically, chemically, actually. The star that exploded to make the material in your body ended. It really ended. There is no version of that star that continued to exist after the explosion. The specific arrangement of matter and energy that was that star was destroyed. What remained was something new, scattered, distributed, different. And from that destruction, here you are, lying in the dark, breathing the oxygen of long-dead stars. Your heart-pumping blood made rich with iron that was forged in the silicon-burning cores of massive stars. Your bones built from calcium scattered by explosions. Your neurons firing signals along axons made of carbon that has been through stellar interiors and interstellar space, and the billion-year journey from supernova remnant to protoplanetary disk to young Earth, to the first organisms, and through 4 billion years of evolution to arrive at this moment in this body, in this dark. You are the inheritance of 7 minutes. You are the consequence of a star that burned too bright and too fast and died too soon, and in dying made everything. The universe is not small, it is not quiet, it is not safe or gentle or arranged for anyone's comfort. It is vast and violent and ancient and creative all at once, and it has been doing this, building, destroying, rebuilding, enriching for 13.8 billion years without pause. And somewhere tonight, in a corner of some galaxy, a core is crossing the Chandrasekhar limit. The collapse has begun. The clock is running. 7 minutes. We are here because of them. We breathe their oxygen. We carry their iron in our blood. We are built from the scattered wreckage of stellar deaths that happened long before the sun existed, in places we will never visit, in events we can reconstruct mathematically but can never observe directly. This is the story of a star dying. This is the story of 7 minutes that shook a corner of the galaxy. This is the story of how violence and creation are, in the universe, the same thing. The shock is still moving. It will be moving for thousands of years. And somewhere in what it leaves behind, the next chapter of the story is already beginning.